right, last session in the last lecture, ordinary lecture. Continue with the manufacturing standard specification for manufacturing of OCTG, oil country tubular goods, covering tubing casing liner. Heat treatment, we talked about why we do heat treatment, recrystallization, compositions of pipes. We talked about what the different compositions and chemicals do to casing. May make a stainless steel, we may have it magnetic or not. We may do different things to make it stronger or have other specifics. Yeah, I think that when it comes to the manufacturing, this is just an information so that I'm not gonna go too much more into detail about it. Rather, we talk more about the other standards, the 10400, and this is an example that is cut from NORSOC D10. Again, this is the performance envelope. We keep within this. This is the industry standard. It doesn't matter if it's call it correct or not. According to me, I'd say that this is not the performance envelope. Why? Because for one thing, a plot like this is not telling you the truth. It's dangerous. On one side, many pipes have a lot more capacity than this. On another side, you need to understand that the software is representing this very correct. Now, the way that they recommend to do this for the landmark software is to use this just as an idea of where you are. Do you have plenty of space? Or if everything is within, you should be okay. But you need always to check on the graphs. They are correct. At least in landmark, they are correct. Whereas there are errors to the von Mises ellipses in landmark, especially on the burst side of things. We have seen this one earlier, and again, this well is put here to reflect that everything is hung in the top. So during drilling, of course, there are not much thermal forces. So basically, the forces are not too significant as per se. You can talk about the kick and so on, but normal drilling loads not that demanding. If you put in fracturing, then yes, then and well interventions, those loads can be extreme. And sometimes even setting the design basis for some tubulars. But normally it's the production loads and reflecting that the tension would be very, very high in the top, and there's very little going on in the bottom, all up until a point where you start to heat it up, right? Then if it tries to expand, you're gonna see some compression in the bottom and less tension in the top. Yeah. All right. What we see inside this plot is actually a master student back in 2014-15 that made a casing design application in Excel. This is a plot from that one. They even modeled a temperature plot. There were 3 of them put together that worked on this. Very, very good product, actually. Temperature model, of course, limited to be correct for water. You need all the input for the thermal properties of different compounds of yeah, hydrocarbons and so on in order to make it very good. And you need to also be able to see well, the phase envelopes, right? When does it go into gas and what kind of thermal changes takes effect in that. The part that is important for us, we see curves here, and they are going from the top of the well all the way to the bottom. The full string would be represented in the three curves that we see here. And we see tubing leak is the one in top. And then we see gas migration in the green and full evacuation in the burgundy one, going outside the primary design envelope. So you'll have a lot of compression and collapse. And we can imagine that the lower part would be in the lower part of the well is down to the left of full evacuation, and up to the right would be the top of that string, whichever string this is, probably the production casing. Yeah. So this is how we do analysis in this to give a quick understanding. Um, Again, from Norsok, there's an error, as said. The green line is not it's not possible that it goes outside von Mises. So that's something that Norsok should consider the next time they issue this plot. Elastic collapse, that is a straight line going all the way to the actual stress. And we see the different types here. Yield strength collapse would follow the von Mises for collapse, and in part 2 that's the green line, and part 3 that's the horizontal straight line, because as said, it doesn't it's not influenced by actual stress at all. Conductor type pipes, high DT ratios. And that part has never been reflected in any software for casing design as I see it. Yeah, we have discussed this plot before, what it is and what it means. Again, for burst, this is also kind of an error. When it comes to, yeah, well, the difference is the 0.875 between the blue and the von Mises touch point, because Barlow calculating the burst pressures is done without taking any actual stress, right? It's only valid in one point, and that's following this graph here up. It doesn't really, it's not valid to the right or to the left, even though we extract that line normally in the design envelopes. Yeah, and zero stress, actual stress would mean where this axis crosses the von Mises, right? Because that in that point there's no actual stress, so they should fall together, and the difference would be the 0.875, the wall thickness correction. Here is the formula itself, the standard itself. Now, what it recommends is triaxial designs for everything. Yeah, it's very clear on it, and basically everything relates to yield. There is a rupture design, triaxial, ductile rupture. It's at the end here where the pipe is rupturing, like we talked about, which is it has its purpose, but you cannot use it for design. Not now. It's a reference. Yeah, I talked about the von Mises. Barlow, it is okay for thin-walled pipe. That's not what Barlow said in his publication in 1836. He was thinking it was a thick-walled calculation. This is what the standard is saying. The derivation of the formula to Barlow is incorrect. Barlow formula has been retained because it happens to represent the thin wall approximation to the biaxial von Mises Lamé. It's a triaxial design, like we talked about. Failure. So it's a coincidence. And that's fine. Now here, if you now take all the statistical data for wall thickness that is listed in the first, well, the first time published in 2007 of ISO 10400, you'll find that the minimum performance, if you make a normal distribution of the wall thickness of pipe, you'll find that there's nothing going below 0.90. What is this, 65 or something, or for this one, for the seamless casing, it's the same. Yeah, and if you follow the absolute minimum that the normal distribution give you, it's still at 0.94, 95. So the 12.5% that is older than from 1950, it's kind of, it hurts. I feel it hurts when I have to use it. I have to answer for the whole industry, which probably I'm not able to, but I'm gonna try to make something, an assumption. It works, like the Volkswagen Beetle. It's a Volkswagen Beetle thing. It works. Yeah, and again, this is how the triaxial design that we made it at NTNU. It's the Lubinsky from 1975, actually, where you put the Lamé and the von Mises together. You end up with these curves and a movable ellipsis. Yeah. And here is what the standard is saying about collapse forces. It still keeps the API in front. We talked about this, and what I did, I said early today in the first session that I was going to say a little bit more about this collapse method. In this table, all the constants are derived because their only variable is the yield. And H40 has a yield of 40,000, so you plug it in and you get these specific constants. And these constants go into the calculation of the borders between the different collapse modes, right? So first you find these constants, F1 through F5, you plug them in here and you find your border. And then you need to know, okay, what dt ratio do I have? You compare it to the limits between these modes, and then you pick your correct collapse mode to calculate. Let's say that your DT ratio is below the limit between plastic collapse and transition collapse. Then you choose the plastic collapse if it's within that range between the limit here and here. Basically, you put in the numbers here, the DT ratio, and you put in the values for these factors. Now, the sigma yield E is a corrected yield strength, and I think it comes here. Yes, here it is. Here. I'm sorry that these slides they were not there on Tuesday. What I did, I inserted the original slides for you guys that have fallen out, and I reissued that in an email. I think it was yesterday, and also I uploaded a video like this one that we're making now in class, discussing these things a little bit more in detail and the sequence of how you do this. So it's listed there in that PowerPoint. Now, what you see here and what you can see is that the axial stress, the sigma A, and the internal pressure also. So that is involved. This is what was made as an addition in 2015 to the API standard, and you put in the original yield strength, and out comes this one that supposed to be correcting for axial stress. It compensates for some axial stress, which in effect makes a curved line. The more axial stress you have, the more it curves. And again, it should never be below the 1 Mises. Yeah. All right. We will now talk about casing wear. We know that casing, the drill pipe would stay on the high side because it's in tension most of the length of it, whereas parts would be in compression. You lower the weight on the bit in order to have some weight on bit and in order to have the possibility to drill. Unless you slack off some weight, there's no weight on bit and you will not be able to drill. And that's the part where the well is in compression, it will be on the outside. Everywhere else, the normal part is on the high side of the well, where it's in tension. Of course, there would be special cases if you drill with the very, call it tortuous well, that the tortuosity is so extreme that and corked that the stiffness of the string will push it to the outside. You have to think about and be a little bit mindful about what the software do. But the base case is what is tried to be put up in these drawings, and it puts this drawing with a question mark because simply it's incorrect. Yeah. In a curvature, we may see something like this. And casing wear is bluntly put, calculating the energy impaired by rotating tool joints to the casing wall along the casing string, and you divide this by the amount of energy required to wear away a unit volume of casing material. That's kind of a very definition as per se. Yeah. And we don't get universal wear. The casing, the drill pipe stays in a spot. You may have oscillations and vibrations in the string, but it wears in a certain area more or less all the time. The only point where it kind of goes all along the circumsphere will be very close to the neutral point. But of course, again, there could be special cases where I'm wrong, but that's the standard case is what I am referring to. And that comes from what we just talked about. The string stays on the high side where it's tension. Um, Types of wear mechanisms. There's basically only two body wear mechanisms that we are going to look into, and typically that takes effect. Let me put it very simple. Here you have the drill pipe and you have the casing. There's also talks about a three-body wear mechanism where you have, for example, cuttings in between. It's not a very relevant discussion. Why? Because the casing wear calculations and models made, they are all based upon testing in a jig about what 30 years ago, something like that, 30, 40 years ago, and they are set up in a specific formula, and you put in your operational parameters, and out gets a result. And it's quite okay, that result, if you do everything correct. But looking into the details of what kind of wear you'll have, galling is abrasive wear. That is the one main wear type that we get in normal conditions. Whereas to the left, galling, that's 13% chrome type, and that's adhesive. It looks like you have taken a piece, like a, yeah. If you're going skiing and you put the wrong stuff under your skis, the snow sticks. Yeah, and that's what happens when you use the wrong thread compound and you try to make up two pieces of stainless steel. You tear off a portion of that of one of them, and it sticks to the other one like snow under your skis. Yeah, that's the best explanation for guys who have never seen this. That's the 13% chrome and other type, which makes the model that exists in the industry not valid at all for 13% chrome. And again, of course, the only valid model that I know of is the one we made here at NTNU. Again, it is in a drawer. If you guys have a business you want to do, come and talk to us. And we also have this test rig in the basement here, identical to the one that made the original calculations and models that we're going to look into now. Yeah. Polishing, grinding, machining. There are plenty of details to go through for those who are interested. Basically, what you're looking at here is the derivation of the theory. The volume removed per unit length is proportional to the frictional work that is done. And the frictional work per foot divided on the specific energy required to remove 1 cubic inch of the material. That's the E, which is a standard. A number, a specific number. And the frictional work done per foot, F, is the same as the normal force, the friction factor, and the sliding distance. And the sliding distance is the point on a piece of pipe like this, and how far it travels down the well. Yeah. What we say and what we use is a wear factor, and that's the frictional factor divided on the specific energy. And our formula at the end of the day is basically coming down to the volume removed is the wear factor times the normal force times the sliding distance. This becomes very simple in that way. But it's not that straightforward because wear typically is not linear. We see this type of wear, a wear groove, a crescent type ball loss. And that means that at some point there is a point load type contact. The drill pipe tool joint, specifically the hard banding on the tool joint, would rest on the inside of the casing, and the wear would be very high because the force the force is the same, but the pressure changes because of the contact area, right? So in the beginning, it's like one of those heels of those very nice dressed women, extremely like a pointy heel thing, and then as the area grows, the normal force is the same, so but the pressure changes, right? So that's why we get this slope that we see here, type behavior, and what this one is called the work function, variable volume, whereas work versus the work function. At the end of the day, what we do is have like a correctional factor that addresses this problem. This is just a test time and the wear group depth in a well, and we see that it slowly goes off. And here is the correction factor that we apply to accommodate this change in pressure, so that the fundament for this is that the wear factor is one number. It doesn't change through the operation. You set wear factor, say 5 in your equation, and you need it to be something else early and something else later. And basically what steel has, standard steel, it has what is called contact pressure threshold. You come to a certain pressure or yeah, and there will be no more wear. It just stops. It's a number. When it comes to 13% chrome material, stainless steel, the contact pressure threshold is not there, which means that these correctional factors and everything else that goes on to correct for a normal steel behavior that they tested once they made the model is just not there. So it's a little bit like putting diesel on a gasoline car, to put it like that. That's what it is. But the industry knows what they're doing. I know many fields been developed with chrome pipe in them and drilling through, and they know how much they can do and what is actually working or not. Basically, what you're coming down to is to run wear logs like caliper or like wall thickness logs to understand, yes, it works. My presumptions were good. Still, what the industry do, believe it or not, they use the wrong calculation. They use casing wear, regular calculations for 13% chrome, which is, yeah, they get the wear factor when they back calculate, ranging from 5 to 50, right? Like, oh, why is this so wrong and strange? Whereas for regular steel, it arrives between, yeah, say 2 to 3 and up to 5 always. Whereas for 13% chrome, it flies all over. Yeah, you get the extreme cases. And from the wear volume, you need to find what is my remaining wall thickness, and that's a geometrical calculations purely. The software looks like this, and this is it resembles the way you put up torque and drag and hydraulic calculations. Basically, you put in what is your hole like. It's part of it is casing and part of it is open hole. And what are the friction factors? You put in the string that you're drilling with. You put in the fluids that are there, and then you have to put in what you're going to do and how much time it takes. Yeah, go ahead. Will the mud type affect the air in a way? Disappointingly little. That's the answer. Yeah, it does, but not a whole lot. Yeah, operational parameters you go into detail with, and then you can do some fine tuning with the wear model and the wear factor. 5 is a good one to start with, unless 13% chrome, of course. Yep. This casing wear software has the really strange name, casing wear. It used to be seaware, and it has been many names. What is kind of funny, if you go to the history of Landmark, you'll see that, well, I believe most of it is there, but the origin of the Landmark drilling design software is actually quite, they bought pieces here and there and they put it together over time. So, but now they are modernizing, if I'm not mistaken. That has been said for years now, and there has been changes and upgrades. Yeah. Wear factor modeling, non-linear, wear factor 5, casing, strength model, API, torque and drag. We use stiff string. Stiff string is adding. If you don't use stiff string, the drill pipe will be looked at as a rope, which gives you quite accurate calculations. But the stiff string is supposed to add the steel's resistance to bending. So it will give you a little bit more accurate normal forces. Now, I have the problem that I don't trust any of these stiff string models. They are behaving weird, I think. So, but it could be just me not looking, analyzing it enough. It could be that. But again, always be critical to what you see in a software model until you know exactly what it does. Yeah. Yeah. Software output, wear versus depth. You need to know along the whole string what has been going on with the parameters that you put in. You will need to know the collapse strength and the burst strength for every meter. Yeah, and you can also see the side force for the depth. Yeah. It's quite a comprehensive software visualizing how the string behaves, where it's compression, where it's tension, how the string is supposed to be in the well. Kind of cool. Not necessarily entirely correct. You need to be. One question that comes up is dogleg severity override, right? Because you plan and you have a mathematically perfect well path, what kind of dog legs will you actually have? How well does this represent that? So you need to be mindful again. And will the string actually look like this? The way it tells you collapse strength versus depth in the well, where there's a dog leg at around 1100 meters. I guess here you see that it kicks off, the kickoff point. You see that the graph actually goes like this and then goes down, and here is the collapse strength at its lowest. The wear is going to give you what, 1700 psi collapse strength in that dog leg. and then it goes up, and then you have a little bit of wear, general wear. This would be the tangent portion of the well, and then it fades off. Burst strength is the same. Profile of the graph, lowest at the dog leg. You can see here that that typically the casing wear would tell you a little bit about how how much dog leg and where to put it is good for you, right? You put it shallow, the tension is extremely high in the drill string, and it will eat of your casing. Whereas if you keep your dog legs mild and try to push them down, you will get less wear. This would be the side force. Yeah, modern calculations. This is the collapse recommendation in Appendix F233 in the standard 10400. It picks up it looked. This is a work where they collapsed 4,000 pipes, and they compared 11 calculation methods. Which one will be accurate? Simply because the API method that the industry is using is not accurate. It's just safe, which is why you keep it, right? But it's not accurate. It's not telling you what is the actual well integrity in the well. It doesn't say that. It's a minimum performance with a whole lot of safety factors built in here and there. So whereas if you want to really know when does my casing collapse, you need to go to one of these methods, and the one that is the most accurate according to the standard is this one, Clear and Tamano. It is what is called an ultimate limit strength calculation. It tells you when it collapses, not the minimum performance. All the input parameters to that collapse calculation, it's not just the yield strength and geometry, but it's the yield strength and then the ovality of the pipe, the eccentricity of the pipe, the residual stress. Remember when we do heat treatments, what is the residual stress in that pipe from the work that you have been doing to it? The accurate wall thickness, and then the product that you get out is the collapse pressure. These have different probability distributions, and the end is going to look like this. So P50 will give you a collapse resistance of 11,400 psi. And that matches quite well the graph that we saw earlier. Remember the collapse graph that this pipe manufacturer showed us, and the API being quite below. You can go to two standard deviations as we do in anti-collision for drilling, and then you're going to come down here somewhere, 9,600 psi. That would be your performance that you're going for. As a here is where it collapses, and then you can say, let me add a safety factor or design factor of 10%. Then taking away, what would that be? Say 10,000, 1,000 psi. So then you're at 8,600 around here. You see, nothing's gonna collapse here, more or less. Nothing. So you can, or you can see even 3 standard deviations and go down way down here. Probability for collapse is extremely small, right? Yeah, and still you're given a much higher collapse resistance than what the API is going to tell you. Traditional API method that we have been detailing in this class. Now, yeah. As a side note, up until today, the manufacturers they gave you only these very rough values, and to get these type of values for a batch of pipe, normally the operators would never ask for it. What is coming now would be a lot of wall thickness measurements, and what we can do now is to transfer data per joint. Imagine that you're purchasing 100,000 pipes in different sizes every year and install in your well. Still, with today's data technology and digitalization, you can get individual data for absolutely all these pipes, and you can have all this data for every single piece of pipe, and you can use modern calculations. And I just see that the future well integrity model or well planning model, it should have the API that is safe, and that's what drilling engineers do. On the other side, when things are critical, you use the modern calculations to add to it to see, okay, where am I at? What is my absolute end value, right? Let's say that you do an unplanned slot recovery. You say, I'm going to use this well now to hit that target. But the API, it tells you, no, that's not going to be possible. Then you go to this calculation and you see, what is my real strength? Yeah. So that's what the industry can save a lot of money on and still know what's going on. Yeah, the work group that made this, and it's a little bit embarrassing. They actually have dedicated in this standard, both API and ISO, they are dedicated a full page. But I think it's like 20 reasons why you're not going to use the API collapse calculation that is in the front that the industry is using. That's kind of neat and interesting. Yeah, we're not going to go into it. Here is a full overview of the appendix. The appendix is almost more interesting than the front section of this standard, to be honest. You find a lot of extremely interesting stuff if you are a geek and you like pipes. Trust me. Yeah. All right. I think actually we are there, but we have 1 minute to talk about other important techniques and conditions. It's inner surface yield, through wall yield is the thing. And what I forgot to mention, API, and going back to our curve, I don't know if we have that one again somewhere. I think I saw, yeah, here it is. This one, in category 1 here, that's not a true collapse. When you reach this limit, you reach yield. And you reach yield on the inside of the pipe. So again, it's not going to tell you when the pipe truly fails. It's just going to say that you have yield on the inside of the wall. The pipe is going to stay the same. Yeah. And you also need through wall yield here before it starts to deform. Buoyancy of tapered strings. You put up one of these calculations and you're going to be busy the whole exam. Yeah. Temperature affects the yield strength. Remember that. Remember that forever. Because you may get disappointed whatever you do, even if you drive your own car, the engine is going to be less. Yeah. Let me see what we're talking. Yeah, that's a quick and dirty method for that some people did in the field. I would be extremely cautious about that one, but it's still there. Yeah, there was a question in one of the earlier classes. There are no standard providing model for worn pipes. No software does that. But again, well, what you do and what they say in the industry is that 1% wear equals 1% reduction in collapse rating, up to 30% wall loss. And that's relating to the API calculations, not to the real ones. Of course, we had to do something about that at NTNU. I mentioned that before. The extremely clever, talented Mr. Andreas Tegland and his paper SPE 205,500. You see his stress concentration factor model here versus Kuriyama, and that it's more accurate. This is for worn pipes, and it's valid for absolutely all collapse modes. Again, if you guys want to do business, let's talk. It's in the drawer. Yeah, we could not do well-field development. Still, it's literature. We could talk probably for the rest of the semester. But fortunately or unfortunately, I don't know. This is the end of about that. This theoretical part. We will have a session down in the dungeons later on. I'll call for it, and you guys will tell me if it's good time or not. Yes, we are. I hope that in 2 weeks or 3 weeks, something like that. Yeah, so that we can also do something about the exercise at the same time.
2 exams the week of 26th to 30th.
Yeah. Guys, what I hope that you can talk together. Let me know what you think about the exercise. We were supposed to talk about the exercise today, but I think it's quite simple also with the theory and the material you have. And I'm not going to be very strict on the submission time at all. So for me, you can just keep it and you can talk and you say, we want to submit. That's fine. I'll do that and correct it. Basically, I think that, we'll do it simple. Yeah. All right. If you have questions, I'm available on 2 emails from now on. So just let me know if there's anything.